Welcome to Algorush. We use databases every single day, but have you ever stopped to wonder what's really going on under the hood? Well, today, we're going to pull back the curtain and look at the actual blueprints for how our data gets stored. It's some seriously brilliant engineering.
You see, every single decision in database design boils down to the physical reality of the hardware it's running on, and for decades, that reality was the good old spinning hard disk. The big enemy there? Slow physical movement. A little arm had to literally fly across a spinning platter to find your data. So reading things in order was super cheap, but jumping around randomly? Oh, that was painfully slow. Then, solid-state drives, SSDs, came along and just completely changed the game. No moving parts, sure, but they brought a whole new and kind of weird set of rules with them.
So faced with this challenge of slow, random seeks, engineers came up with an architectural masterpiece. This design was so perfectly suited for that environment that it basically defined what a high-performance database was for an entire generation. Okay, let's get into it.
And that masterpiece is the B tree. This data structure was literally born to conquer the spinning disk. Its whole job, its entire reason for being, is to take a potentially chaotic mess of data and organize it so well that what should be a slow, random lookup becomes just a handful of quick, efficient reads. It's all about minimizing those expensive physical movements.
Yeah, you can think of it like a perfectly organized digital filing cabinet. You start at one single spot, the root page, and from there, you just follow a few pointers through these branching nodes, and boom, you found exactly the record you're looking for, even in a massive data set. And we're talking just a handful of disk reads to do it. The magic is really in its balanced structure. It guarantees that the path to any piece of data is always super short and predictable.
So here's the crucial part to understand. What made the B tree so brilliant for its time is that it performs updates in place. It goes right to the spot on the disk where the data lives and changes it directly. For the world of spinning hard drives, this was absolutely perfect. But then the hardware changed. The physical reality of storage got completely upended.
And that brings us to the solid-state drive, or SSD. Right away you're thinking, great, no moving parts, so those slow seeks are a thing of the past. Problem solved. Well, not quite. It turns out the SSD has its own unique and, frankly, kind of bizarre limitation. Okay, so get this. On an SSD, data gets written in these small chunks called pages. But here's the weird part. If you want to change the data on just one of those pages, you can't. You first have to erase the entire, much larger block that the page lives in. And that block might contain hundreds of other pages that are perfectly fine.
And this one simple physical rule, well, it creates a massive problem for our beautiful, elegant B tree. Remember its whole in-place update strategy? All of a sudden, that perfect strategy is terrible. Changing just a few bytes now requires this huge, inefficient operation.
This whole mess has a name. It's called write amplification. That elegant in-place update we love so much, now it forces the drive to read an entire block into memory, change that one little page, and then write the entire block back down. It is just wildly inefficient. And worse, SSDs can only be erased a certain number of times before they wear out, so this process literally burns through the life of the drive way faster. The old blueprint, it was completely broken. The foundation it was built on had been ripped out from under.
So what do? You need a whole new way of thinking. A new architectural philosophy, one that doesn't fight against these weird rules of flash memory, but actually embraces them. And this new philosophy is, well, it's stunningly simple. The core idea is never, ever modify data in place. Instead, you just write the new version of the data to the end of a file. It's like adding a new entry to a journal or a log. You don't go back and erase old entries, you just add new ones. Don't update, just append.
And this is the central idea behind something called the log structured merge tree, or LSM tree. Look at how this works. All new data gets buffered in a small table in memory. Once that's full, whoosh, it gets written to the disk as a brand new, unchangeable file. Then, in the background, a process is constantly tidying up, merging these little files into bigger, more organized ones. The key here is that every single write to the disk is a sequential append. It completely sidesteps that random write penalty of SSD.
Now, this don't change anything philosophy is also the driving force behind other cool structures, like FD trees. That stands for flash disk trees. An FD tree uses a small B tree, but it keeps it in memory. This is called the head tree, and its job is to soak up all the incoming writes. Once that head tree gets full, its contents get flushed out to the disk as another immutable, sorted file.
But how do you search across all these files efficiently? Well, FD trees have a really clever trick. They use these things called bridges, smart pointers that link related items from one file to the next, which massively speeds up searches. But you see, the goal is exactly the same. Find a smart way to tame the SSD.
Okay, so now we have these two brilliant blueprints, one for the old world of spinning disks and one for the new world of SSDs. So how do you decide? Which trade-offs are you willing to make? Because that's what this is all about, trade-offs. Are you optimizing for reads, for writes, for memory usage? Thankfully, there's a really neat framework to help us think about this.
It's called the RUM conjecture, and it gives us three big dials we can turn when we're designing a storage system: read overhead, update overhead, and memory overhead. But here's the catch, and it's a big one. You can't turn all three dials down to their minimum setting at the same time. Turning one dial down almost always forces another one to go up.
Let's look at our two blueprints through this lens. B trees, they crank the read dial way down. Finding data is super fast, so read overhead is low, but the cost is high update overhead. Those in-place updates are expensive. Now, LSM trees do the complete opposite. They turn the update dial all the way down. Appending new data is incredibly cheap, but the trade-off is that the read overhead goes up, because to find the latest version, you might have to look in a bunch of different files. You just can't have it all.
So, what's the big takeaway here? It's that there is no single best solution. There just isn't. The right blueprint is always a direct response to the hardware it runs on and the workload it needs to serve. It's this beautiful dance between software design and the hard, physical constraints of reality.
And you know, this constant cycle of innovation where these brilliant software ideas are sparked by the physical limitations of our hardware, that's what makes this entire field so incredibly cool. And it makes you wonder, right? As storage technology keeps evolving past flash to persistent memory, or something we haven't even dreamed of yet,